All right, everyone, welcome. For years, AI felt like something out of a sci-fi movie. But it's not science fiction anymore. It's right here, in our operating rooms, and it's starting to change the way we practice anesthesiology in some really profound ways. So today, we're going to dive deep into how AI is shaking things up, from predicting risks before surgery to helping us make split-second decisions. We'll explore what this means for us, for our patients, and for the future of our specialty.
So here's what we've got on tap. First, we'll get on the same page about what we mean by AI in our world and look at the latest research trends. Then, we'll walk through the entire patient journey, pre-op, intra-op, and post-op, to see AI in action. We'll also zoom out to see how it's optimizing the entire smart operating room. And finally, we'll get real about the challenges and what the road ahead looks like. Sound good? Let's jump in.
Okay, part 1, the new paradigm. You might have heard this term floating around, Anesthesia 4.0. And it's not just about flashy new equipment. It's a really fundamental shift, a new way of thinking that's all driven by data. But before we get into the cool applications, we've got to make sure we're all speaking the same language. So let's quickly break down the core tech that's behind all of this.
The easiest way to think about this is like a set of Russian nesting dolls. The biggest doll is artificial intelligence, or AI. That's the whole big idea of making machines smart, right? Mimicking human intelligence. Inside that doll, you've got machine learning, or ML. This is where things get interesting. Instead of writing a bunch of if-then rules, we just feed the machine a ton of data and let it learn the patterns for itself. And then, the smallest, most powerful doll inside that one is deep learning. This is a special type of machine learning that uses something called neural networks, inspired by the human brain, to find super complex, subtle patterns. Think about it. It can look at a photo of a patient's face and predict a difficult airway. It's that powerful. These are the engines driving everything we're about to talk about.
Now, the workhorse of medical AI is something called supervised learning. The name gives you a hint. We have to supervise it. The key word here is labeled data. Imagine you have thousands of patient charts, and on each one you've already written the answer, like, this patient is an ASA2, or this patient developed a post-op complication. You feed all this labeled data to the algorithm, it crunches through everything and learns the patterns that connect the patient's info to the final outcome. Once it's trained, you can give it a new patient's chart and it'll predict the outcome for you.
So, what does this look like in practice? A perfect example is automating the ASA score. Think about it. We can take a massive data set of patient records where an expert anesthesiologist has already assigned the ASA score. The model chews on all that data, the comorbidities, the lab results, the patient history, and learns the incredibly complex relationships that lead to a specific score. The result? You get a tool that can assign an ASA score to a new patient almost instantly, with an accuracy that's right up there with a human expert. This isn't about replacing us. It's about creating consistency and saving valuable time.
Okay, but what happens when you don't have all those neat labels? What if you just have a giant, messy pile of data? That's where unsupervised learning comes in. It's totally different. You just dump all the data into the algorithm, say continuous physiological data from thousands of surgeries, and you tell it, go find something interesting. It's not predicting anything specific, it's a discovery engine. It looks for hidden structures and can find clusters or groups of patients that we might never have thought to look for on our own.
Let's make that real. You could feed an unsupervised model tons of patient response data. It might come back and say, hey, I found this weird little group of patients over here. They all seem to have a really delayed emergence when you use this particular anesthetic. The algorithm doesn't know why. It can't explain the physiology, but what it's just done is hand us a brand new, data-driven hypothesis on a silver platter. It points us where to look next, and that's the first step toward truly personalized anesthesia. And now for the third type, which is maybe the most futuristic, reinforcement learning. Forget labeled or unlabeled data. This is all about learning by doing. The best way to think about it is like training a brand new resident in a simulator. The AI agent, our virtual resident, tries something, like giving a little bolus of propofol. It then looks at the patient's response, like the BIS monitor. If the BIS gets closer to the target, it gets a reward point. If it goes the wrong way, it gets a penalty. Now, imagine it does this millions and millions of times, way faster than any human could. It learns through trial and error what the absolute best sequence of actions is to keep the patient perfectly stable. It's learning a strategy.
And this is exactly the kind of tech that's behind those closed-loop anesthesia delivery systems, sometimes called robo-anesthetists. These systems aren't just following a simple algorithm. They are powered by reinforcement learning, They are constantly making tiny adjustments to drug infusions, observing the patient's unique physiological response, and learning in real time the optimal dosing strategy for that specific person in that specific moment. It's truly adaptive and personalized medicine.
All right, so that's the high-level theory. But I know what you're thinking. What's actually being done? Is this just a bunch of cool ideas, or is there real research to back it up? Well, a major systematic review that looked at the last 5 years of literature, from 2019 to 2023, gives us a fantastic snapshot of what's really going on.
So, the researchers started with this massive pool of papers, over 90,000 of them. But after they filtered for quality and relevance to perioperative medicine, they ended up with just 22 studies. Now you might think, only 22, that's not a lot. But that number actually tells us something really important. It means the field is moving past the initial hype. We're now in a phase where only the really rigorous, high-quality research is getting through. It's about evidence, not just experiments.
And if you look at the publication trend over those 5 years, you see a really interesting pattern. There's this initial peak of excitement, and then a slight dip. Now that dip doesn't mean people are losing interest, quite the opposite. It's a classic sign that a research field is maturing. We're moving beyond the low-hanging fruit, the simple, hey, look what we can do studies. Now, researchers are tackling the much harder, much more time-consuming work of clinical validation and real-world implementation. The problems are getting tougher, and the research is getting better.
So, what are all these smart people working on? Well, the data couldn't be clearer. Look at this breakdown. The vast majority of these studies, we're talking 16 out of the 22, were focused on one single massive problem: predicting how long a surgery is going to take. This tells you that the first big push for AI in our field wasn't about some flashy clinical tool. It was about solving a fundamental logistical nightmare that affects everyone in the hospital.
And when you dig into how they're predicting surgical duration, a rockstar model emerges. Just look at this table. Study after study, year after year, you see the same name pop up as the top performer, XGBoost. That stands for extreme gradient boosting. You don't need to know the math behind it, but you should know why it's so good. It's an absolute beast at handling the kind of messy, complex, spreadsheet-like data that we have in our electronic health records. It just works.
Okay, enough about the research papers. Let's get back to the clinic. How does all this technology translate into what we do every day? To make sense of it, let's follow a patient through their entire perioperative journey.
So the journey has 3 main stages, as we all know. We're going to start at the very beginning in the preoperative phase. This is where AI is really starting to change the game by helping us answer that one crucial question with way more precision. Just how much risk is this particular patient facing?
In the pre-op clinic, AI is giving us some incredible new tools. For instance, there are algorithms like My Surgery Risk that don't just give you a vague high risk or low risk. They can predict the actual probability of 8 different specific complications with really high accuracy. But the one that really blows my mind is airway prediction. We're now seeing deep learning models that can analyze a simple photo of a patient's face and predict a difficult airway better than our traditional tests, like the Mullen-Patty. They're seeing subtle anatomical clues that the human eye just can't pick up.
Okay, now let's step into the operating room. This is where AI's role completely changes. It's no longer a planning tool. Now it becomes our real-time co-pilot, crunching a constant stream of data to help us see around the corner and anticipate what's about to happen.
And predicting intraoperative hypotension is the absolute perfect example of this shift. Think about our standard practice. It's reactive, right? The blood pressure drops, the alarm goes off, and then we treat it. But now we have tools like the Hypotension Prediction Index, or HPI. This isn't just looking at the current blood pressure. It's analyzing the arterial waveform in real time with machine learning to predict the likelihood of a hypotensive event minutes before it happens. It gives us this golden window of time to be proactive and prevent the pressure from ever dropping in the first place.
And this proactive mindset is being applied all over the OR. There are models like Prescience doing the same thing for hypoxemia, giving you an early warning. In the world of regional anesthesia, computer vision is a game changer. It can look at your ultrasound screen, identify the nerve, and highlight it for you, helping to guide your needle. I want to be really clear about this. None of these tools are designed to take over. They're decision support. They're there to boost our own situational awareness when things are moving fast.
All right, the procedure is done, but our job isn't. The postoperative period is just as critical, and AI is playing an increasingly important role here in managing recovery and, crucially, catching complications before they escalate.
So our patient is now in the PACU, and we all know the challenge here.
It's a busy environment, and we need to figure out which patients are on a smooth path to recovery and which ones are silently starting to head for trouble. AI can help us sort that out and focus our resources where they'll make the biggest difference.
Here's a look at what's being done in the PACU. We've got models predicting length of stay, which helps with patient flow and staffing. And here's a really key finding. When it comes to predicting post-op complications, the best models are the ones that use the full picture. Data from both pre-op and intra-op periods. They're way more accurate. And perhaps most importantly, we have algorithms that can just watch the vital sign trends in the background, looking for those subtle patterns that suggest a patient is starting to deteriorate, flagging them for us long before a crisis hits.
Okay, so far we've been focused on the individual patient. Now let's zoom the camera out and look at the bigger picture, the entire operating room suite. This is about using AI not just for clinical care, but to optimize the incredibly complex logistics of the OR. The whole dance of scheduling, staffing, and getting the right resources to the right place at the right time.
I don't think I need to tell anyone in this room about this problem. Predicting surgical case duration is, let's be honest, a nightmare. Whether we're using a surgeon's best guess or just a historical average, we're often wrong. And that one wrong number kicks off a whole cascade of problems. Scheduling conflicts, staff staying late, and patients getting delayed for hours. So, how can AI help fix this mess?
Well, the solution is to stop guessing and start predicting with data. AI models, especially that XGBoost we talked about, can be trained on tens of thousands of past cases. They look at everything, not just the procedure, but the specific surgeon, the patient's BMI, even things like the number of levels in a spinal fusion. And here's the kicker. The research shows that when you create a model that's specific to an individual surgeon, the accuracy goes through the roof compared to those generic hospital estimates.
And this isn't just academic. The benefits are real and they are measurable. We're talking about a randomized controlled trial that showed using these models directly leads to patients waiting less. We're talking about a significant drop in the average error of predictions. And studies have shown this can lead to a more than 10% improvement in overall OR efficiency. Think about what that means for your department's budget, for staff morale, and for patient satisfaction. It's huge.
But unpredictable case times aren't the only thing that throws a wrench in the works. We have two other major headaches: the PACU becoming a bottleneck that backs up the entire system, and those incredibly costly and frustrating last-minute case cancellations. Can AI help us manage these as well?
You bet it can, and the strategy is exactly the same. Get proactive. For the PACU, models can predict which patients are at high risk for a long stay. Knowing this ahead of time means the OR manager can be strategic about the case order to avoid a logjam late in the day. For cancellations, other models can look at an upcoming case and flag it as high risk for being canceled, maybe because of the patient's history or the type of procedure. This gives the pre-op team a heads up to call that patient, double-check everything, and try to save the case before it's too late.
So as you can see, the potential here is absolutely massive. It's easy to get excited, but we also have to be realistic. There is a huge gap between a cool research paper and a reliable tool that you trust and use every day in the OR. So let's spend a few minutes talking about the very real challenges that are on the road ahead.
The hurdles really fall into two big buckets. The first is all about the data. You've heard the saying garbage in, garbage out, and it's never been more true. Our EHR data can be a real mess, and getting clean, high-quality data is a huge first step. Plus, we have all the privacy and security issues to worry about. The second bucket is clinical adoption. How do we actually get these tools to work with our clunky hospital IT systems? And maybe the biggest question of all, how do we get clinicians to trust a black box? If an AI gives you a warning, you're going to want to know why. And that's a major technical and psychological hurdle we have to clear. And that's before we even get into all the legal and regulatory questions.
And that really leads to what I think is the single most important takeaway message about the future of AI in our field. This isn't about building machines to replace anesthesiologists. That's not the goal. The real vision, the one that's both powerful and safe, is to create human-in-the-loop systems. These are systems where the AI acts as an incredibly powerful decision support tool, but the human expert, that's you, is always in control, making the final call.
And that is what we mean by Anesthesia 4.0. It's a future where our hard-earned clinical experience isn't replaced, but is amplified by the power of data. It's about shifting our practice to be more predictive, more proactive, and more personalized for every single patient. It's an incredibly exciting time to be in this field, and honestly, we're just getting started. So I want to leave you with one final question to ponder. As these incredibly powerful tools become more and more integrated into our daily work, what does that mean for our specialty? How does it change what we need to teach our residents? How do we redefine the core skills and competencies for the next generation of anesthesiologists so they're not just users of this technology, but are the ones who will lead its development and ensure it's used wisely? It's something we all need to be thinking about.